All right, folks, so let's continue on our journey to implementing a priority queue. So what we're going to do here is first start talking about data structures. So data structure is the basic idea of how do I store something, right? The idea and the hope here, I guess, is to say that however we choose to store our data, it's going to be a way that aligns very closely with what we want to do with that data. If we do it that way, right, then hopefully things will be very fast. So we're going to introduce the idea of a heap, which will be a way to store data that lines up pretty well with the idea of a priority queue. So in order to get there, what do we need to talk about? We need to kind of start by reviewing a couple of concepts. The first concept is the notion of a binary tree. So a binary tree is a tree, but where every node, right, has at most two children. So on the right-hand side here, this is a binary tree, right? Notice if I look at 2, which is the root, it has 2 children. If I look at 5, it has 1 child. If I look at 6, it has 2 children, right? Every node here has either 0, 1, or 2 children, right? That's what we call a binary tree, right? So a tree where every node has at most 2 children is called a binary tree. This is something you've probably seen before. Well, you should have seen before in your prerequisite class like SER222, probably your prerequisite math as well, right? Your discrete math course. So this is a binary tree. Second thing you've seen, right, is the notion of a binary search tree, which is a binary tree, but with an order imposed. Here, right, the order doesn't really matter, on the different labels on the different nodes, right? I can put whatever numbers I want there. That said, if I adhere to a certain rule, right, specifically we say left side is smaller than a node, right side is greater than a node, what I end up with is a binary search tree. So if I look here, right, I notice I have 8 here as my root. Well, I have something smaller for the left-hand side and something larger for the right-hand side. And if I look down, drill down to that tree, I have the same thing going on, right? Over here, 14, left side is smaller, right? It's 13. Over here for 7, right, left is smaller, right is larger, right? So 6's left was 4, 6's right was 7. So smaller stuff. So basically the rule is here, right? You're looking at a node, the left side has to be smaller, the right side has to be greater, right? If those two things hold, this is a binary search tree, which have lots of applications, right? One that you guys have hopefully seen before is basically to find elements, right? It's easier, right, to find, something in this tree, right, if I have it sorted in this way, right? So if I want to know something like, hey, how long does it take me to, how does this collection, right, does this tree contain the number, contain the number 1? It would take me a lot of time, right, in that first tree to answer that question because I need to go and visit every single node and figure out, hey, do any of these nodes equal 1, right? Versus if I was looking at a binary search tree, I'd like start at the top and basically say, hey, this 1 is less than 8, so let me go to the left, try to find something smaller, and then I'd be like, oh, hey, this is where it exists, right? It's much easier for me to find something in a tree, right, if I have some sort of idea of where things are supposed to be stored. So yeah, that's a binary search tree. So these two things you've hopefully have already seen. So let's now introduce our new concept, which is that of a heap. So a heap is a little bit more loosely ordered than a binary search tree, right? So a binary search tree has basically a left and a right rule, right? So if I have, let's say I have 4 values. Let's say I have 1, 2, 3, 4. I don't put those in a binary search tree. There's a ton of different ways I can put them in, right? As long as I preserve, the rules that say smaller things have to go on the left, larger things have to go on the right. Let's see, and then my 1 should go over here. Right, so I'll try to keep all my rules in order. Right, so this is a BST. Now for heap, we'll have this slightly easier to follow rule where we basically say the parent has to be larger than the children. So in this case, right, I could actually draw the following. I could draw 4 on top, and then 3 over here, and 2 over here, and maybe 1 is underneath 3. Right. So in this case, right, my rule is basically going top to bottom. So I have large stuff over here, small stuff over here. Right? Versus over here it was kind of a left-right rule, right? Small goes to the left, large goes to the right. So I have kind of these, let me kind of box these a little bit, right? So this over here is a BST. This over here, right, this is a heap, the right-hand side drawing, okay? So I have different rules, right? Top to bottom instead of left to right. And this will be a lot easier to manage for us than having that left-right rule. Because somehow that left-right rule, it's like I have, I'm treating my children different, right? Left has a different rule than right. For this other mechanism for having a heap, basically it's just top to bottom. That's how the rules applied, right? So I don't have to care left to right child, just top to bottom. So it'll be easier to work with. So yeah, so we're going to start thinking about, so in terms of like a structure, maybe they could help me store a priority queue, right? So kind of our idea, right, when we're trying to implement a priority queue is that we want to pick some underlying structure for it, right, that'll make it easier for us to implement, right? That's usually kind of one of the first steps you want to do when we implement a new data type, right, or when we implement a new ADT. So yeah, we got these two options. So let's think about it for a second. Here's some questions for you guys. So looking at that right-hand side tree, I'll read the first question. Where is the largest element stored? What do you guys think? Well, here the largest element is going to be at the top, right? So the largest one is over here. That's kind of nice, right? So if I have this rule, right, that my parent's always larger than my child, well, kind of by the transitive property, the largest one has to be on top because it's the only one that can, kind of cope with, right, having everything beneath it. Right? Everything that's kind of smaller will be, has to be forced down to be underneath it, right? It's the only thing that kind of can, stand on top. So yeah, largest element will be on the top. Let's see, for a tree with n elements, how many nodes are between a leaf and a root, right? So we're asking basically, for a tree here, right, there's, n things here, right here, n is equal to 4. How far is it, right, to start at the top, right over here, and get down to, a leaf, right? That's a question for you guys. Think about it for 1 second. What do you guys think? So here the answer is going to be log n, right? It's going to be, well, maybe plus or minus 1, right, depending on how it is. But generally it's going to look something like a log. We hope it looks like a log because it's a binary tree. We're also making this. We also have to make some assumptions or some knowledge in there about like the sort of the balance. And we'll talk about that in a minute. But in general, right, the hope is, right, is if your tree is properly structured, it'll probably look like log n, right, log 2 sub n even, because it's like a binary tree, right, kind of splits, splits, looks like a log thing, right. So that'll probably be our height for the tree. If we ideally, right, we can get there, and that actually would be pretty nice, right. Because if it's log n height, that means that I can find my way to any node from any other node, right, in log n time, right? Very, very nice property to have. So this is our basic idea, right? This is the idea of a heap. Again, it's a data structure, right? It's a tree, but it has this binary tree, right? But it has the rule that basically a parent has to be larger than both of our children, right? That's kind of what we call a maximum heap. And that's what we'll stick with here, right? Obviously, there's also the idea of a minimum heap, but the parent has to be smaller than the children. But for us, we'll just stick with the idea of a large one.